Hello, this is Group 61. I'm Xiaojing Huang.
And I'm Wenxin Li.
In this project, we aim to design a tomato leaf disease detection model. We first make observations on the dataset. We can see that in the samples, the disease patches are usually tiny and has low contrast. Also, the classic distribution for all the labels is highly imbalanced. This will make our model hard to learn from real classes. Thus, for this task, we take YOLO VA as the backbone, which is a classical model situation for most detection tasks. And we will introduce attention mechanisms and class weighting into the basic model. To be specific, we start with standard YOLO VA backbone and added the following customization. For the original convolution block, we added an optional SEBlock after the three original modules. Multi-scale convolution is added for capturing both small and big patches. Blocks are updated with all the convolutions blocks turning SE on. The backbone is also updated, replacing standard CSP to the enhanced version, and adding multi-scale convolutions in the shallow layer. The neck remains unchanged. We update the hand by enabling SE for both convolutions blocks, a dry out layer for regularization, and classifiers based on weights. We also added loose functions enhancement with classic weight and focal loose. As we changed, it's observed that the new model converges much slower than the original model under the same training setting. We figured out some reasons. One is that the enhanced loose computing is focusing too much on the real classes, making the model conservative. Too much attention also leads to over-regularization. The dry-out layer will reduce the ability to detect the objects. Thus, we remove part of enhancement as we keep testing, and the final structure is like this. We keep optional acid blocks in convolution module. In CSP blocks and backbone, we reduce the amount of attention, only enabling SEBlock for deeper stages. In the end, we enable SE for one convolution model and integrated classifiers inside. The classifier is also set to MIDA. Here is a general structure diagram of our model.
So for the evaluation matrix, except for box position and NAP50, we select the third one to be recall. While box position focuses more on the proportion of correct prediction, recall focuses on how much we discovered among all the diseases, which complements all perspectives of the model performance. So in actual agricultural settings, missing diseases can be costly, so improving detect rate is very valuable. And also, considering that the disease patches can be small, missing them won't affect precision much, but recall will become lower. So evaluating recall can help us discover this kind of hidden problems. For the initial stage training, when applying early stopping, the model will reach the criterion at around epoch 100 with 0.7 recall rate. When training full 200 epochs, 3 matrix will rise to about 0.8 to 0.9. And here we have a few test cases. The solid line represents actual labels and the dashed line are predicted boxes. The model can detect some patches missing in the label and also very small patches. For the post-training stage, we implement a Fourier-based loss. The feature map is transformed to frequency domain, and then we take 40% as high-frequency cutoff. For high-frequency content, we penalize loss of energy in the very fine detail band, and for diversity loss, we encourage the spectrum to be broad instead of being peaky in a narrow band. We aggregated them to get the final Fourier loss. It is multiplied with coefficient alpha before added to the total training loss. So compared with the initial stage performance, result becomes better. It met the criteria by about epoch 95, which is a bit earlier than the base version. And for full training, it also achieves about 1 to 3% better results. The model is now able to detect smaller patterns like fine spots and subtle color variations. We can see improvement in result after applying Fourier loss, as it enables the network to preserve and respond to texture features in mid-high frequency band, rather than low frequency, smooth region, and global shapes. But the improvement isn't very significant. This is because we already have attention blocks and class bias in the model, which provide enough regularization in the beginning. Thus, Fourier loss can only give limited improvement. So that's the end of our presentation. Thank you for listening.
Thank you.